Hello, this is Yashveen. In this video, I'll be solving paper 2 variant 2, October November 2022 AS level chemistry. Question 1. Species such as ammonium ion, carbonate, and phosphate ions are examples of molecular ions. A. Ionic and covalent bonds both involve an electrostatic attraction between different species. Identify the species that are electrostatically attracted to one another in an ionic bond. So in an ionic bond, you've got ions that are involved in the bond, anions and cations of the opposite charges. So those are the species involved in this bond. In a covalent bond, the attraction is between the bonding pair of electrons and the nuclei of the two atoms involved. So for example, if you've got two atoms over here and a pair of electrons over here, this pair of electron is not only attracted to the nucleus on the left hand side, but it's also attracted to this nucleus over here, and because of this attraction, neither of the atoms will completely gain or lose the electrons. They will be shared. B. Complete table 1.1 to show the total number of protons, electrons, and in the molecular ions. So you've got 3 of these. The number of protons will not change in any of the ions. So let's start with the ammonium ion. The total number of protons would be the number of protons of nitrogen plus the number of protons of hydrogen atoms. Since there are 4, you will add up all 4 of them. So the atomic number of nitrogen, or the proton number, is 7. The proton number of hydrogen is 1. Since you've got 4 atoms, you would multiply that by 4, and that's 11. Now you've got a charge of +1, which means this ion has 1 less electron than the total number of protons, which makes the number of electrons 10. Moving on to the carbonate ion, you would add up the proton number of carbon, which is 6, and then to that you would add 3 oxygen atoms, so that would be 8 multiplied by 3. This is 30. Since you've got a charge of -2, that means there are 2 more electrons in this ion than protons, which would make that 32. And then phosphate ion, you would add again the atomic number of all of the atoms in this ion. The proton number of phosphorus is 15. The proton number of oxygen is 8. Since you've got 4 of these, you'd multiply 8 by 4, and that's 47. Again, here you've got a charge of -3, which means there are 3 more electrons than protons, which would mean that's 50. C part 1. Ammonium ion is a Bronsted-Lowry acid. Define Bronsted-Lowry acid. So this is a proton donor. As you can see over here, ammonium ion has a charge of +1. It can dissociate to form ammonia and a proton. Part 2. When ammonium ion is heated with aqueous sodium hydroxide, a pungent gas is produced. Write an ionic equation for this reaction. So in an ionic equation, you would only involve or write the ions that will react. So you'd start with ammonium ion. Ammonium ion, being in an acid, would react with the basic hydroxide ion, and this would form ammonia, as ammonium ion donates the proton to the base, which would form water. 3. The nitrogen atom in ammonium ion is sp3 hybridized. sp3 orbitals form from the mixing of 1 2s and 3 2p orbitals. Sketch the shapes of a 2s and a 2px orbital on the axis in figure 1.1. So s orbitals are always spherical in shape, and 2px orbital is a dumbbell shaped orbital which lies on the x-axis. And there you have it. D. There are many naturally occurring hydrated compounds that contain the anion, phosphate anion, and you're supposed to name this ion. Whenever you are supposed to write down the names of an ion, you also need to write down the oxidation state, in this case phosphorus over here. So now you want to find the oxidation state of phosphorus. So let that be X, since that's unknown. Oxygen is almost always -2. Now since you've got 4 oxygen atoms over here, to the X, or the oxidation state of phosphorus, you would add the oxidation state of all of the oxygen and multiply that by the number of oxygen atoms. This is equal to the total charge of the ion, which is -3. So X minus 8 is -3, which is why X is equal to +5. So this is phosphate ion with the oxidation state of phosphorus as +5. You'd write that down in Roman numbers. 2. Struvite is a soft hydrated mineral with molecular mass 245.3. The anhydrous form of the mineral has this formula. Calculate the number of molecules of water of crystallization in struvite. Give your answer to the nearest integer. Show your working. So they have given you the molecular mass of the hydrated compound. You can find the molecular mass of the anhydrous compound and then subtract the mass of anhydrous compound from the hydrated mineral. You'd get the mass of all of the water molecules. So let's start with finding the molecular mass of the anhydrous mineral. You would add up the masses of all of the elements, starting with nitrogen. That would be 14 plus hydrogen is 4 multiplied by 1. Magnesium is 24.3 plus 31 for phosphorus, and then 16 for oxygen multiplied by 4 of the atoms, which is 137.3. This is the MR of the anhydrous mineral. You'd subtract this mass from 245.3 to get the mass of all of the water molecules, and that's 108. You divide this by the mass of one water molecule to get the number of water molecules, and this turns out to a total of 6. E. Aqueous hydroxide reacts with 2-bromo-2-methylpropane in an SN1 reaction. SN1 reaction is a nucleophilic substitution reaction between a tertiary halogenoalkane and a nucleophile, which in this case is a hydroxide ion. This molecular ion forms as the intermediate in this reaction. So this is a tertiary carbocation. 1. Draw the mechanism for the SN1 reaction of hydroxide with 2-bromo-2-methylpropane. Include charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. Draw the structures of the organic reactant and the product. So you'll start with a halogenoalkane, and that's going to be 2-bromo-2-methylpropane. Alright. Here you've got that. This is SN1 mechanism, which means this is a two-step reaction in which the first thing that happens is the carbon halogen bond breaks down, as carbon has a partial positive charge and the halogen, bromine in this case, will have a partial negative charge. So this will result in heterolytic bond fission, which means as the bond breaks, both of the electrons in this bond will be gained by bromine, which is why you have a plus charge on the cation over here. And then hydroxide ion, being a nucleophile, will be attracted to this, and a new bond will form between the cation and the hydroxide ion, resulting in this tertiary alcohol. Part 2. 2-bromo-2-methylpropane is a tertiary bromoalkane. Define tertiary bromoalkane. So this is a bromoalkane in which bromine is bonded to a carbon atom that's bonded to 3 other carbon atoms and no hydrogen atoms. Part 3. Organic compound M forms when 2-bromo-2-methylpropane is heated with ethanolic hydroxide ion. Draw the structure of M. So when you've got ethanolic instead of aqueous hydroxide ion, this will result in an elimination reaction instead of substitution. So when halogenoalkane undergoes elimination reaction, it forms an alkene. So here you've got 2-bromo-2-methyl-propane. Elimination reaction will remove not only this bromine atom but either one of the adjacent hydrogen atoms. Let's say you remove this one along the right hand side hydrogen atom along with the bromine atom. This will result in a double bond forming between these two carbon atoms. So this will form an alkene without the bromine and one of the hydrogen atoms. Question 2. The chlorides of some of the period 3 elements are shown in table 2.1. Complete table 2.1 by identifying the bonding shown by each chloride under standard conditions. Use C for covalent, R for ionic, and M for metallic. The bonding in sodium chloride and magnesium chloride is ionic, and that between aluminium, silicon, and phosphorus pentachloride is covalent. The structure in sodium chloride is a giant ionic structure. Aluminium chloride also has giant structure. Silicon chloride and phosphorus pentachloride have simple molecular structures. Oxidation state of period 3 element. So sodium loses 1 electron, giving it an oxidation state of +1. Aluminium loses 3, silicon loses 4, phosphorus loses 5. In this compound, phosphorus loses 3 electrons, so it will be +3. Sulfur loses 2 electrons, so that will be +2. B. Write equations for the reactions of sodium chloride and phosphorus pentachloride with water. Include state symbols in both equations. So sodium chloride, being an ionic compound, is not hydrolyzed by water. It only dissolves in water to form ions. So you start with a solid sodium chloride and end up with its aqueous ions. Sodium having a charge of +1 and chloride ion as well. And then phosphorus pentachloride having a molecular structure simple molecular structure would react with water. Oh, and it's solid in state. Water is liquid form, and it's liquid form, and this would form hydrochloric acid as well as phosphoric acid. Alright, so here you've got 4 oxygen atoms, so you need to balance that over here. Now you've got 8 hydrogen atoms on the left hand side, 3 in phosphoric acid. That means you need 4 more to balance the hydrogen atoms. C. In the gas phase, aluminium chloride exists at equilibrium with its dimer of Al2Cl6 as shown in this equation. Complete the dot and cross diagram to show the bonding in aluminium chloride existing in its dimer form. Okay, so here you've got 2 aluminium atoms and 6 chlorine atoms. So this is how aluminium atoms and chlorine atoms are bonded together in this compound. Now you've got these 2 chlorine atoms. Each one of them will form a dative covalent bond with one of the aluminium atoms. That means each of these chlorine atoms will donate 1 pair of electrons for the covalent bond that needs to form. So let's say the top chlorine atom forms a dative bond with the right hand side aluminium. That means it will donate both of the electrons needed for this. And so the bottom chlorine atom will donate its lone pair to the left hand side aluminium atom. All of the remaining bonds that form between aluminium and chlorine would be normal covalent bonds, meaning 1 electron from chlorine and 1 electron from aluminium. Now you just need to fill out the remaining electrons in the chlorine atoms, and this way all of the atoms will have 8 electrons in their outermost shell. completing the octet. And there's the structure. Part 2, state the effect of an increase in temperature on the equilibrium mixture in equation 1. Explain your answer. So the forward reaction is exothermic, which means the backward reaction is endothermic, and so that is going to be favored by increase in temperature. As the backward reaction is favored, equilibrium will shift to left hand side. D. A 3.3 gram of a period 3 chloride is heated at 500 Kelvin in a sealed flask. At this temperature, the chloride is a gas of volume 250 cm3 and the pressure in the flask is 323 kilopascals. Use the ideal gas equation to calculate the molecular mass of the period 3 element to deduce its formula. Alright, so you'd start with using the ideal gas equation. PV is equal to nRT, where the number of moles is equal to mass over molecular mass. So you can substitute this in the formula, and this means the molecular mass is equal to mass RT divided by pressure and volume. So you start with, alright, let's just get a few values in their standard forms. The pressure is 323 times 10 to the power of 3 pascals. Volume is 250 cm3, which means 250 multiplied by 10 to the power of -6 meter cube. Now we can plug in these values, which means mR is equal to 3.3 multiplied by 8.31, 500 and this is equal to 170. Now you'll look at the molecular mass of all of the period 3 chlorides, and you'd find that the molecular mass of silicon chloride is 170.1. So that means this chloride is silicon chloride. E part 1, an excess of aqueous chloride ion is added to 1 cm3 of aqueous bromine. Describe what's observed and explain your answer. So halogens react by gaining electrons or by oxidizing the other reagent, and they can only do this if they are more reactive than the other reagent. So for example, bromine cannot react with chloride ion because bromine is less reactive than chlorine, or bromine is less electronegative. So in this case over here, no visible reaction occurs and the solution remains as it initially was. No color change occurs. Part 2. Sulfur chloride has molecular mass 103.1 and is a liquid at room temperature. Sulfur bromide has a higher molecular mass and it's a gas at room temperature. Explain the difference in the physical state of sulfur chloride and sulfur bromide. Give your answer in terms of intermolecular forces. The melting point of molecules depends on the forces between the molecules. So the sulfur halide bond is polar, which means there will be permanent dipole forces between molecules of sulfur chloride and sulfur bromide. In the sulfur halide bond, sulfur will have a partial positive charge and the halogen, bromine or chlorine, will have partial negative charge, as these atoms are more electronegative. This will result in a dipole. Now because chlorine is more electronegative than bromine, it will attract the electron pair more strongly, which will create stronger dipoles, and in turn it will also create stronger intermolecular forces, and that's why sulfur chloride will have a higher boiling point, making it a liquid at room temperature, compared to bromine, which is a gas at room temperature. So overall, this means that sulfur chloride has stronger permanent dipole forces because it's more electronegative. F. Bismuth is a dense metal in the same group as phosphorus. Draw a label diagram to show the bonding in bismuth metal. So this will have the same structure as any other metallic structure with positive ions and a sea of delocalized electrons. These positive ions form when the valence electrons will move out of the orbits into the metallic structure, and these electrons enable the metallic structure to conduct electricity when they are free to move. So here you've got the cations and then free electrons or delocalized electrons all over the structure. Part 2, bismuth reacts with chlorine to form this compound, which is a solid at room temperature and melts when heated gently. It reacts vigorously with water at room temperature to form an acidic solution. State the type of bonding and structure shown by bismuth chloride. Explain your answer. So as you can see, it reacts with water, meaning that it's hydrolyzed. When a chloride is hydrolyzed in water, it means that its bonding is covalent, since we saw earlier that as we saw over here, sodium chloride having ionic bonding is not hydrolyzed, it only dissolves in water, whereas phosphorus chloride will get hydrolyzed in water, meaning that it has covalent bonding. We would use the same reasoning in the last answer to deduce that its bonding is covalent as well, and because it melts easily when heated gently, this means it has a simple molecular structure. Question 3. The organic compounds can be distinguished using chemical tests and analytical techniques. A. Table 3.1 shows 4 pairs of organic compounds, and you're supposed to identify a region to distinguish between them, as well as give positive results for the chemical tests and identify which compound shows this result. First one, you've got an aldehyde versus a ketone. So aldehyde, or A1 over here, can be oxidized by an oxidizing agent like potassium manganate to form carboxylic acid. And the change that you'll observe is color change from purple to colorless. It can also give silverware with Tollens reagent or a brick red precipitate with Fellings solution. Okay, both of the compounds in the second row are ketones. However, in B1 you've got carbonyl carbon that's bonded to CH3, which means it can react with aqueous iodine, alkaline aqueous iodine, by iodoform reaction to form the yellow precipitate, whereas B2 cannot do that. In the third row, you've got a ketone and an ester. Ketone or aldehyde, both of which are carbonyl compounds, would give a positive result for 2,4-D and pH, which is how you can differentiate between these two. And it would form an orange precipitate. Between D1 and D2, D1 is a tertiary alcohol, whereas D2 not only has a hydroxyl group but also alkene. So you would differentiate using the alkene part over here. Alkenes react with aqueous bromine, turning the solution colorless. So aqueous bromine would react with D2. Part 2, A1 and A2 are structural isomers. Define structural isomers. These are molecules with the same molecular formula, as in they have the same number of atoms of each element and they have different structural formula. Part 3, give the systematic name of B2. B2 over here is a ketone. You've got 1, 2, 3, 4 and 5 carbon atoms, which means, and also you've got the carbonyl. The carbonyl carbon is in position 3. So this is pentane 3-on. Part 4, deduce the molecular formula of D1. Let's see, D1 over here has 4 carbon atoms in the ring itself. Now each of these carbon atoms is single bonded. So this means here you can have 2 hydrogen atoms as well as these 2 positions. Now the 4th carbon atom is bonded to 2 other groups, which means it's not bonded to any hydrogen atoms. Looking at the structure, you've got 5 carbon atoms, 10 hydrogen atoms and a single oxygen atom, which means the molecular formula is C5H10O. B. D2 forms polymer Z when heated gently. Identify the type of polymer that forms from D2. So D2 has an alkene group, which means it forms an addition polymer. Part 2, draw one repeat unit of polymer Z. Carbon-carbon double bond will form the backbone and everything else will form a branch. So here you've got Z, the carbon-carbon double bond, and the remaining atoms will be a branch in the polymer. So as the double bond opens up, this is how you'll have the repeat unit. Part C, organic compound E contains 3 carbon atoms. E reacts with cold dilute acidified potassium manganate to form a single compound F with molecular mass 154.9. Alright, so it's alkenes that react with cold dilute acidified potassium manganate to form diols. Figure 3.1 shows the infrared spectrum of E and figure 3.2 shows the infrared spectrum of F. So now to begin with, we know that E has a carbon-carbon double bond and F will have hydroxyl group. Both spectra show absorptions between 2850 and 2950 per centimeter owing to the carbon-hydrogen bonds in each molecule. Part 1, use the 2 infrared spectra and table 3.2 to identify the functional group present only in E. Explain your answer referring only to the absorptions at frequencies greater than 1500 per centimeter. Mention the functional group as well as the explanation. So we already know that E has a carbon-carbon double bond, and looking at this table over here, that would provide absorption between this range. And let's try to find that, which you can see over here, this peak falls in that range. So that's what we can mention in our first answer. Use the infrared spectrum of F to identify the functional group formed when E reacts with cold dilute acidified aqueous potassium manganate, which we already know would be an alcohol. So that would be an a hydroxyl group. Explain your answer referring only to the absorptions at frequencies greater than 1500 per cm. So let's look at the absorption range of a hydroxyl group, that is between 3200 and 3650, which you can see over here. And this is a broad absorption which you need to mention as well. The mass spectrum of E shows a molecular ion peak and an M+2 peak of approximately equal abundance at these ratios. Reduce the relative molecular mass of E. Alright, whenever you see an M+2 peak, that means in the compound that you're dealing with, you either have chlorine atom or a bromine atom. Now, because the peaks are approximately of equal abundance, that means this is going to be a bromine atom. If the peaks had a ratio of 1:3, that would have been chlorine. So now we know that E, first it has 3 carbon atoms. There's going to be at least one carbon-carbon double bond as well as a bromine atom. Let's try and see if we can find the formula. So this double bond can be between any of the 2 carbon atoms, and the bromine as well can be on any carbon atom. Now if we had all of the remaining atoms as hydrogen, and we found the molecular formula of this compound, that would be 3 carbon atoms multiplied by the mass, as well as the mass of 5 hydrogen atoms plus the mass of bromine, which is 79.9, and this turns out to 120.9. So this looks like it is the correct structure since it's close to these 2 values. 4. Use the information in 3-part C to suggest a structure for E. So as I mentioned earlier, the bromine could be bonded to any carbon atoms, which means we can have something like this as our structure. You could also draw the skeletal formula, which would look like this. Part 5. Complete the equation for the reaction of E with cold dilute acidified aqueous potassium manganate to form F. In the equation, the oxygen in bracket represents cold dilute acidified potassium manganate. Okay, so we already know when the alkene group reacts with this reagent, it will result in the formation of a diol, which means, alright, so this should be 2 over here, my bad. So this will result in a diol and a hydroxyl group bonding to each of the 2 carbon atoms that were initially a part of the double bond. So now you can deduce the molecular formula of F, which is C3H7BrO2. Alright, so you can write that down over here. And then you'd write the molecular formula of E, which is C3H5Br, and that completes your equation. Part D. C2 can be synthesized using A1 as a single organic reactant. So C2 over here is an ester, A1 is an aldehyde. Use a multiple step synthetic route to form C2 from A1. Identify the relative reagents and conditions and state the organic products of each step. So you form an ester by reacting a carboxylic acid with an alcohol, which means you need to convert A1 into an alcohol as well as an acid, and then react both of them to form C2. And as you can see, you've got 3 carbon atoms in A1 and 6 carbon atoms in C2, which is also an indicator that you use the same reagent to form both alcohol and acid. To convert an aldehyde into an alcohol, you would reduce it. So here you can reduce AI with lithium aluminum hydride or sodium borohydride to form propane 1-ol. And then you would oxidize it with an oxidizing agent like potassium dichromate to form propanoic acid. Then you would react the two in the presence of concentrated sulfuric acid to form ester. So sulfuric acid over here will act as the catalyst. And this was it. We are done with this paper. Thank you for watching.